All right, so for our review session, I wanted to go over Skill Builder 15.8. It's one of the ones that students tend to struggle with a bit more. So the first thing they tell you to do when they give you a proton NMR spectrum is to begin by calculating the HDI. I always tell students start with the easiest stuff and then work your way to the hardest stuff. HDI is easy. So always remember to do your HDI. And then it says, next consider the number of signals and the integration values for each signal. And if you actually walk through the whole guided practice, they talk about how the integration values are just ratios. So you may need to divide by the smallest value to get to your whole number ratios that are more reasonable, and we'll talk about how to do that. And then it talks about how to problem solve your way through a variety of these. So what we'll work on for this chunk of today is 15.23. It's a series of NMR spectra where we're asked to basically uncover the structure for each of the different compounds. So let's work on that in OneNote. So let's do the first one. So in this first one, we've got A. What's the HDI going to be for this? So we double the number of carbons. So we've got 8 times 2 would be 16. We add 2, so that's 18. We subtract the number of hydrogens, which is 10. So that's 8, and then we take 1/2. So this would be a HDI of 4. So that means we have 4 rings and 4 pi bonds. I'm actually going to blow this up even more. But either way, this is really useful to have, and it's simple to do, so you might as well just do that first things first. Next thing I'm looking at is the integration values. Down here, I'm seeing an integration value of 45. That doesn't make any sense if we only have 10 protons, right? So let's try to divide things down. So what I would do is I would say, all right, over here, our smallest value is 9.1. So I'd take 45.1 divided by 9.1, and that's going to be equal to about what? 5. Okay, so we know the integration value is going to be 5 over here. We know this divided by 9.1 is going to be about 2. Same thing over here. If we divide this by 9.1, this is also going to be about 2. And then this is just going to be 1, right? This makes more sense, right? Because now when we add up 5 plus 2 plus 2 plus 1, that actually adds up to 10. So now we've got whole number values that correspond to the number of protons. Does that make sense? So if you're ever stuck on the integrations, just remember the ratios, and you can change the numbers to match the number of your protons just by dividing or multiplying by a constant. All right, so we've got that done. Next thing I would do is I generally start out in this region of the NMR, primarily because this region over here can be a lot harder to interpret. So normally I kind of look in this region and I'd say, all right, this peak right here, it's about 7-ish. So what peaks normally show up in the 7-ish range? Well, if you're really stuck, you can go to your handy dandy cheat sheet. You can say, all right, around 7, that's probably going to be my aromatic protons. All right, so let's go back and make a note in here that this is going to be an aromatic proton, and we know that there are 5 of them. So what does that tell us? Well, it tells us we must have an aromatic ring. Safe to assume it's just going to be a benzene-like ring. And we know that we must have 5 protons coming off of it based on the integration value that we just determined. However, we don't know what this R group is right here. Does that make sense so far? All right, other thing I would look at is the HDI of this aromatic ring is what? 4. So another trick we could say is based on this, there are no remaining rings or pi bonds. Does that make sense? Okay, so now we can go through this and start piecing it apart, and we can say, all right, what's really left over? So we're pretty confident in this chunk right here, right? But what's left over from the molecular formula? What are we missing? I'd say we're missing 2 carbons, right? Because we got 6 carbons in the ring. But molecular formula, that's C8. Yeah, so I'd say 2 carbons. All right, if we look at our hydrogens, we've got 4 coming off the ring, which means we're missing 5. Or sorry, we've got 5 on the ring. So we've got 5 hydrogens left over, and we have 1 oxygen left over. All right, so I'm just kind of subtracting clues from my original clue, right? All right, so now let's go back and look at this. If we look at this peak over here, this looks like a 2H triplet. This looks like a 2H triplet as well. And then over here, we've got a 1H singlet. All right, so my question for you, let me put this triplet in here, is we can just pick one of these. I oftentimes try to go after the easiest ones first. So what do you think is easiest to interpret, the triplets or the singlets? Probably the singlet. So let's just focus in on this. You don't have to, but that's generally what I do. Question is, what could give you a singlet that's 1H? Yeah, no neighbors, or it has to go through a non-carbon atom to find a neighbor. So in this case, I would say maybe an OH would be a good one, right? So if we think about this, maybe we've got an OH group somewhere in here. All right, so now let's go back to our leftovers. So I'd say, all right, we're going to erase that 1 oxygen. We're going to now go down to 4 hydrogens. And we've got that done. So I'd say that makes sense. How could we maybe confirm this part with other spectroscopy techniques? IR. What would we expect in IR? A big smooth tongue, right? So in this case, we could do secondary testing to confirm that with IR too. All right, but for right now, I think that's a pretty solid guess. That would give you a 1H singlet all of the time, all right? Doesn't matter what. So now we've got these leftover triplets in the middle. Both are 2H. We've got 2 carbons, 4 hydrogens. I'll give you another hint too. Over here, we said that this must be kind of a sticky end attached to something. And then over here, in fact, let me draw it in. Over here, this alcohol must be attached to something, right? Can we just attach these 2 pieces together and call it good? No, because then we wouldn't have any place to put these, right? So it's implying that the 2 carbons must be in the middle somehow. So what do you think could make sense that could account for those 2 carbons and 4 hydrogens? What's that? So maybe just 2 CH2s? Yeah, absolutely. So we could go ahead and we could say RCH2, CH2, R. So maybe this is our missing piece where these are the sticky ends. So it kind of makes sense, right? Because if we think about this CH2 has 2 3-bond neighbors, it'll be a triplet. And it'll integrate to 2. Same thing with this one. It'll be different, and it'll be 2H. All right, so to me, it seems like we've got all these puzzle pieces. We just need to snap them together now. Make sense? How many of you feel pretty confident snapping them together? Hopefully you should. So for this one, the correct answer would look like this. So I will say when I work on these, at least personally, I use a ton of scratch paper. I just try to write down as many clues as possible and try to work through it slowly. The biggest problem I ran into when I was working on these as a sophomore was my brain would freak out and be like, I can't get it, I'm gonna fail. You just have to go slow, sometimes take a break and go back to it later and see if you can pick up any of the other clues. But try to always remain positive as you're working through these. Does that make sense? All right, want to do the next one? All right. I'm just gonna slide this over so it's out of the way. All right, so we've done that one. Let's go ahead and do B over here. So over here, let's do the HDI really quick. So somebody said the HDI is 1, so the easiest thing to do is double the number of carbons, that's 14. Subtract the number of hydrogens, that's now at 0. Add 2 and take 1/2, so that's 1. I agree. All right, next things first. Let's do the integration values. So over here, it says we have 14 protons. Quite clearly, the integrations don't add up to 14. So what would make the most sense? Yeah, if we did whole number ratios, I'd say 65.7 divided by 10.1 is going to be equal to 6, right? And then this divided by 10 point, oops, sorry, it should be 10.8. Then that divided by 10.8 is going to be 1. So now if we look down here, I'd say, well, we've got a 1 to 6 ratio. That adds up to 7. 6 plus 1 is 7, not 14. But it's okay, it's still a ratio, it's an easier to manage ratio, right? All right, so now we got to kind of start figuring out, well, what in the heck is going on that would give a 1 to 6 ratio like this? And I generally start with the easiest to interpret peaks. So what I would do is I'd say, let's kind of focus in on this peak. We've got a doublet, or at least what looks to me to be a doublet there. How many 3-bond neighbors must that set have? 1. So this doublet implies that we have 1 3-bond neighbor next door. Okay, so let's think about it this way. So right here, this is going to be our neighbor. And then this is going to be the proton that we're looking at. In fact, sorry, let me do it like this. So this is going to be our proton of interest. And we said that the neighbor can only be 1, right? Because if there's only 1 neighbor, that's what gives a doublet. However, we know that the proton of interest, there's actually much more than 1. There must be 6. So what we could do is we could say, maybe we've got 2 methyl groups that are next door, which makes sense, right? Because when we think about all of these, they're all going to be equivalent to one another, right? Why is that? They're in the same chemical environment, right? All right, so now over here, we must have some other R group kind of hanging off right there. All right, so I'm just going to erase this over here, and I'm going to say proton of interest is going to be a doublet. And we know that it's going to have 6 protons in that set, right? All right, so now let's go over here and say, what about this one? So that purple one, what will it integrate as? I'd say it'd integrate as 1, meaning only 1 proton in that set. What will it be split as? Septet. Okay, which makes sense over here, because when I'm counting, I'd say 1, 2, 3, 4, 5, 6, 7. You see those 7 peaks in there? So I'd say that's probably our septet. All right, so immediately, right off the bat, we've gone ahead and we've identified all of the peaks in our NMR. Make sense? But I'm seeing a problem, right? We've only accounted for 7 of our protons when we really have 14. So what do you think could account for there being truly 14 protons rather than 7? What do you think? A mirror image? Yeah, so maybe we have a plane of symmetry. So we could go over here and we could say double equals symmetry. Does that make sense? Because if we have a plane of symmetry, the left-hand side is going to be the same as the right-hand side. Yeah. Yeah, that's a good question. So right now we're only focused on the symmetry of the protons. because that's what we're looking at for the NMR, is just protons. All right, but that's a good point. Where do you think the oxygen would be in order for it to be symmetric, though? It would have to be in the middle, right? Okay, so let's kind of make sense of this. Okay, so we've got symmetry. Over here, this whole thing is really what we would call an isopropyl group, right? Make sense? We know we've got two of these. What are we missing too? What's left over? Okay, so left over, we have one oxygen left over. Let me spread this out. What else am I missing? One carbon. All right, let's also keep track of our HDI, right? Because our HDI was 1, yet we haven't shown any evidence or rings or pi bonds. So what do you think could be the case here? Or what do you want to try? Carbon-oxygen double bond? Okay. So let's try to piece this together. We know we've got the HDI that we need to account for. So maybe this fragment is a CO double bond with 2 R groups hanging off. All right, so now the story is starting to come together. How many of you think you've got a good idea of what this is? Yeah, probably the isopropyl groups coming off either side. Okay, so now we can go ahead and we can say, well, this makes sense. If it were this, that would give us all of the clues, and it makes sense because if we cut this in half, the left-hand side is the exact same as the right-hand side, which is making everything kind of come together. Does that make sense? So these are a little bit tricky when you're working through some of them. All right, let's do the next one. So this is C, proton NMR C10H14O. So let's do the HDI for this one. So HDI for this one, we double 10. That's the number of carbons, that's 20. We would add 2, that's 22. Minus 14 would be what? 8? Divided by 2 would be 4. So we got an HDI of 4, so not too bad. I'll give you the formula, so don't worry about memorizing it. All right, next thing's next. When I look at my integrations, it looks like 2 to 2 to 1 to 9. If we add all of those up, adds to 14. So luckily they already did that work for us. It looks like the whole number values are correct here. So we don't need to adjust any of those. All right, next thing's next. I would look kind of at maybe some clues. So does anybody spot a clue that they see in terms of chemical shift, meaning ppm? So aromatic ring. Aromatic protons normally show up 6 to 9 ppm, right? So I'd say this is a big clue that this is going to be an aromatic set of protons in there, right? In this case, 2 different sets, each being doublets. All right, so let's try to make sense of what's going on here. I know that there are 4 aromatic protons. So let's take a look at what's going on. So maybe it's like this, where we have 2 protons like that. That's one option. I'm going to slide this over. Or maybe it's like that. That still has 4 protons coming off an aromatic ring, right? Or, let's do one more. I'm going to just draw over this because it's easier. Maybe it's this. All of these 3 options have 4 aromatic protons, right? So my question for you is, do you think option A, option B, or option C is the correct one based on what we're seeing in the NMR, and why? You think A is? Why? Why A? Yeah, in A we've got symmetry, meaning there's only 2 signals, right? What about with B? How many signals would we expect for B? We'd expect 4, right? Assuming A and B are different, yeah. All right, what about with C? 4. So in this case, we've already narrowed it down into being this sort of regiochemistry based on the fact that there are only two signals. We can also look at it further and we'd say, well, what will this show up as? It'll be a doublet because there's only one neighbor. Same thing with this. There's only one neighbor, so there'll be a doublet. Make sense? All right, so we've got this figured out. Now we've got to figure out what in the heck is coming off either of these ends right here. But for right now, that's pretty good evidence, so I'm going to tuck this kind of in the corner over here, just so we have that available as a clue. All right, next thing's next. Over here, you can see they've kind of blown it up, and it looks like there's this broad peak. Looks like a singlet to me. You can't really see any splitting in there. What could cause a peak to get broad? Hydrogen bonding. So just like with IR, we see peak broadening in NMR as well. So I'd say, all right, this is a clue that it's H bonding because it's broad. All right, so we've got some options for H bonding. We could have an amine, we could have an alcohol, something like that. What do you think this is likely going to be? Do you think it's going to be an amine? No, there's no nitrogen in the molecular formula, right? So this is a big clue that over here, this must just be an alcohol, right? It's really the only option that makes sense given our molecular formula that only has oxygen in it. All right, so that's really the only thing that makes sense here. All right, now we go to the next one. We've got a peak of 9. That's a big singlet. So what do you think could account for a peak of 9? 9 protons all being the same? What if we have CH3, 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 right? If we think about this proton set here, right? It's going to be the same as the other methyl groups. So I said methyl groups spin around like helicopter blades and kind of blur out on NMR. In this case, all 3 methyl groups are like a set of propeller blades on propeller blades. So they're all averaging out to be the same. So in this case, this makes sense. All right, so now let's try to figure out what's going on. We've got 6 carbons in the aromatic ring. We've got 4 carbons over here. So it looks like we've counted all our carbons. Do we have enough hydrogens? Yeah, I think we counted all the hydrogens. We counted the oxygen, right? All right, so how do we snap this all together into one cohesive picture? Well, I would say it would make sense that we have a tert-butyl group coming off one side and then an OH coming off the other. So this must be the structure for that unknown compound. Does that make sense? Do you want to see me walk you through one more, or do you want to try it on your own?
Maybe one more.
One more? Everybody's like, this would make my skill builder so much easier if you just do it. All right.
we might have 2 options on the exam, quiz or exam. So we have either integration values, or we're given the number of items, right?
Yes. So the question was, will you be given the number of protons directly or the integration values? I'd say double check either way.
Okay.
Yeah. It's important to remember that the integration values are just ratios. So you can change them if you want to. All right, next one. A little bit trickier. So let's do the HDI for this one. All right, so we've got 4 carbons. I double that. That's 8. I would subtract, or sorry, 8. I would add 2. That's 10. Subtract 6. That'd be 4 divided by 2. So this is HDI of 2, right? All right. Next things next, I would look at the integration values. Clearly, they're a little bit off. So I would say we would need to do what here?
I think they're all 1, but values, the ratio.
Yeah, it looks like a 1-to-1-to-1 ratio, but we've got 6 total protons. So I would say this is probably set to 2 to 2 to 2, right? So that ratio seems to add up to our molecular formula. So I'd say that kind of clarifies it. Oftentimes students freak out when they see these numbers, so just ignore those. Just get it to a close whole number ratio then. All right, so now we've got that set. All right, so now let's take a look at the chemical shifts. This one gets a little bit trickier. So over here, I'm seeing a triplet between 4 and 4.5. All right, so let's go to our cheat sheet and try to figure out what shows up in the 4 to 4.5 region. So I'd go over here and I'd say, all right, what in the heck shows up between this region? Well, it could be a lot of different things. It could be a proton coming directly off of an alkene, or it could be a proton that's attached to a carbon that in turn is attached to an electronegative atom, right? It's kind of unclear at this point. We're kind of in between both of these. I wouldn't necessarily lean one way or the other here, but I'd say it could be one or the other. All right, so let's go ahead and go back. Where'd my thing go? Did I lose my page? I feel like I'm going crazy now. Didn't we just have a tab with our whole sheet? Oh, it's right there. It was just blank. Whew, thank goodness. All right. So if we look over here, I would say this clue is that it's either close to very electronegative atom, or it's going to be something like this. All right, so that's a reasonable clue. What do you think, though, based on the fact that we have 2 oxygens? What do you think is most likely? I would say it's probably close to an electronegative oxygen because we have 2 oxygens that we need to account for anyways. So I would say I'm leaning more towards this. In addition, if you go back to that NMR study guide, one trick you can do is use this sheet. So do you remember when we talked about this in lecture? One thing I always notice is that when we start getting into values that are around 4, that often means that it's an oxygen, it's a group that's attached to the oxygen of an ester. So that shifts things all the way to 4. So that's another clue I might kind of pull into this situation. Okay? So it's attached to an ester. All right, so let's try to figure out what's going on. So I'm just going to call this an R group. Then over here, I've got a carbon. So these 2 protons are attached to that ester. It could explain why they're showing up at about 4.3 ppm, right? Make sense so far? All right, so now we could say, well, they're at 4.3 ppm, but they're being split as a triplet. What does that imply about the neighbor? It has 2 neighbors, right? So over here, I'd say that implies that this neighbor can only have 2 protons on it, and then something else must be coming off this end that's not a proton, right? All right, that's pretty good though. I think that's a really solid clue that we have so far. So I'm just going to kind of shrink this up and put it right there. Okay, so we've got that kind of figured out. We've accounted for both of our oxygens. We've accounted for 3 of our carbons and 4 of our hydrogens. So what are we really missing right now? Okay, so left over is a ring or pi bond based on our HDI, right? We're also missing 1 carbon, right? And then what else are we missing? 2 hydrogens. All right, so now we've got to kind of figure out what's going on here. So let's go to our remaining parts. It says we have a triplet and then a triplet of triplets, meaning multiplet more or less. It's hard to interpret. Does anybody have an idea for how they think this might be all connected together? Yeah, it could be a ring. So let's take a look at this. So maybe this R group right here and here is the same carbon just looped around into a ring, right? That could account for the HDI of 2. So let's try to figure out, well, what in the heck would this ring system look like? Oh man, let me zoom in more. I can't draw that small. So if we think about this, this has 4 carbons in it. It's got 2 oxygens, and it's got 6 hydrogens. So over here, we said that these protons are going to be this set, right? They're the protons on the carbon that's immediately attached to the oxygen of an ester. All right, now let's go over here. We're getting colorful now. What will these be? Those red ones. It'll be a triplet. And if we go to the sheet, let's go to our study guide. We've got a CH2. So I'd say, all right, we've got a CH2. And in this case, it's attached directly to a carbonyl group. So I'd say, all right, we want to take this 1.2 benchmark value and add 1. So it should add up to be about 2.2, right? So let's go back and check that triplet. Is that triplet close to 2.2? Yeah, it's pretty close. So I think that makes sense. So we'd say, all right, this red set is going to be right there. That leaves us with 1 more set of protons. Why is this showing up as a triplet of triplets? Does anybody know why it's not showing up as a pentet? For those blue ones? Yeah, because the neighbors aren't all the same. They'll actually split to different magnitudes, kind of like I was talking about over here, where I said, all right, in this example, we had a proton split by 1 neighbor type and then separately by another neighbor type, and that led to this doublet of doublets situation. Same thing is happening over here. The red protons, being one set of neighbors, are different than the green protons. So we're getting this complicated splitting pattern. Yep. Yeah, so if you look at it, it looks pretty similar to a pentet. I would give you credit if you said a pentet too. Yeah.
I guess we would look at that and look at the formula.
Yeah, so in this case, a doublet of doublets, however it's, or sorry, a triplet of triplets, however they're so close to a pentet, I'd be fine with you calling that a pentet as well. Does that make sense? So these are a little bit tricky. So if you are stuck, don't always think that it has to be a double bond. It could be a ring system as well. So don't neglect rings. That's a good curveball that they threw here. All right, how about this? Why don't we have a brief break and let everybody work on this one, and then we'll check our work. So over here, I'd say question mark. And over here, I'd say question mark. But over here, I'd say this is a quartet.
That's a quartet? What?
It's a quartet.
It's really hard to see, but let's zoom in. Yeah, it's kind of fuzzy. If you look in your book, hopefully it's higher quality, but that's a quartet. And then what is this one? Triplet.
Okay, the triplet is obvious, but the quartet.
In the book, it's lower base.
Yeah, in the book, it's higher resolution than my copy and paste. I'll also make an announcement in class tomorrow that the last skill builder in this chapter is it's about a form of spectroscopy we're not going to get into. It's called DPT, tests for carbon-13, so you can skip that skill builder. So it's more trying to find whole number ratios. So let's say you divide by your lowest value, it's 1.5. And maybe we double everything by 2 to get it back to the number. Yeah.
So here's like an issue that is flat review.
Okay.
So does this mean all things are reviewed then?
Yes. Yeah, they're all automatic. Which means you only have one other thing. Oops. Sorry.
Okay, then like it's separate piece, yeah?
Mm-hmm. Yep.
So this problem is number 8.
Mhm.
So there's only 4 signals on the
So they're all kind of blotting together.
okay.
And that happens sometimes, especially with aromatics. It's not that you don't have all of the peaks, it's just that they're all stacked on top of one another.
But for this one,
Would
it's
this
3
consider the
signals,
nice
right?
one?
Yeah, so for this one, we would expect 3 signals, but they just happen to overlap really tightly. Yeah.
Is that,
They only have
what
more common in the rings, but it's not that it only happens in rings.
And we expect to have three different signals, but in reality, they are stacked up together. We'll know that.
Yeah, however, the big clue is that we have 5 protons making up that set, which implies that we have an aromatic ring with 5 protons and 1 attachment point.
No, like that was just, you just give us that graphic, at the intro of the chapter that, like, oh, and here's that, and we wouldn't know without looking at that, right?
Yeah, so that's a good point. Oftentimes I ask you to predict, but our predictions are always just good guesses. Experimental data might differ a little bit. That's fine with me.
Are we going to be this miserable on our appraisal exam?
Are you going to be this miserable?
Yeah, I cannot tell what's going on here.
All right, let's maybe come back together and work on this then. All right, HDI for this one. Did anybody figure this out?
5.
What was it?
5.
5. Okay. That's good. We got HDI 5. All right, over here, hopefully we figured out the integration. In this case, it's going to be 2 to 3 to 2 to 3. 7 is going to be our least common denominator, so divide everything by 7 and you'll figure out the whole number ratios. So this works out pretty well because now we've got the set number of protons figured out. Okay, so that's not too bad. All right, next things. Over here, what is showing up in this region? Aromatic. All right, and we know that we've got 5 aromatic protons, which is useful. Okay, what that tells us is that we must have 5 protons off this ring, which means we must have 1 attachment point coming off of the ring. Does that make sense? Because if we had 2 attachments coming off the ring, then we would only have 4 protons. So in this case, this makes sense. All right, so good clue here. All right, now over on the right-hand side, we've got a quartet that's integrated to 2 and a triplet that's integrated to 3. What do you think this could be? Well, let's think about it this way. What's a good group that reliably integrates to 3? CH3, right? So a methyl group always integrates to 3 because it's got 3 protons, right? All right. However, it's a triplet, which implies that its next door neighbor must have how many protons attached? 2. All right. So over here, now it's starting to make sense, right? This triplet is right there. What do you think this quartet's going to be? Well, it makes sense that this quartet would be these 2, right? Because it integrates to 2. It's got 3 3-bond neighbors, gets split into a quartet. All right, so now we've got this kind of taken care of. And let's go ahead and start looking at our leftovers. All right, I'm counting an HDI 1 left, right? Because the ring took care of 4, but our HDI was 5, so we still have an HDI of 1 to consider. All right, what else? We've got 6, 7, 8 carbons. We really have 9, so we must have 1 carbon left. And 1 oxygen. All right, what about hydrogens? Got 5 off the ring and then 5 on the other side, so it looks like we have all our hydrogens. All right, so again, our leftovers are giving us a clue. We've got an HDI 1, meaning we have 1 ring or 1 pi bond left over, and we've got a carbon and oxygen. What seems reasonable here? So we could say this is a big clue that maybe we've got a CO bond in there, right? That makes sense. All right, and the CO bond would have to have 2 attachment points. Whoop. So I'm going to go ahead and, oh my goodness, my pen. Slide this over. Must have 2 attachment points here and here. So now we've got all of our pieces that we can link together. And I would say, all right, this makes sense. I must have an aromatic ring immediately attached, would be my CO double bond. And then I would have my ethyl group over here. Does that make sense? So we're kind of linking all of these puzzle pieces together to find our final answer. Yeah.
How we know about the carbon oxygen level one immediately linked to the this?
That's a good question. So we know that these two pieces right here and here can't be linked. Why? Well, yeah, we wouldn't have any place to put our CO double bond, right? So the only logical place where it could go is in between those two pieces. Otherwise, we wouldn't have any attachment points to link our remaining atoms onto. All right. So last one, I don't know if we'll really have time to work on this, but I'll at least let you get started looking at it since it's a good skill builder problem.
So on the last question, we just glossed over the two question cluster.
Yeah, so that's a good question. Over here, we kind of skipped the signal splitting. In some cases, it's not always clean, and I will say aromatic signals sometimes get a little bit confusing for a few reasons. One is they quite often overlap, meaning the signals are so close to one another that they physically overlap on top of one another. The other reason, it's more complicated, is that I told you that only 2 and 3 bond neighbors could split a proton, right? The reality is in aromatic systems, 4 bond neighbors do a little bit of splitting too. But it's really, 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 really minor, but major enough to kind of muck up the whole picture a little bit. So don't worry too much about that. I'm not going to purposely try to trick you or anything.
And in this question, the single splitting doesn't matter in the software cluster, right?
No, in this question, the signals splitting doesn't matter so much as understanding that there were 5 protons in the aromatic region. That's a big clue. All right, so I'll let you work on this one a little bit. What's the HDI for this? Okay, so HDI of 0. Okay, if we look at the whole number ratios, it looks like we need to divide everything by 13. So down here, this looks like this should be 1, this should be 2, this should be 6, right? And what's this one? 3? So yeah, that would add up to 12. So that's our whole number ratio that seems to work well. All right, I'll give you a hint over here too. We've got a singlet that's integrating to 1. What do you think that could be? An OH? Yeah, we got an oxygen in there. So maybe this is our ROH. So that's a good clue. All right, then we'd have to find the remaining pieces. Yep.
What about the others?
Other singlet. Yeah, okay, so you're saying what about this one? That's a good one. So let's take a look at this one. So over here we've got integration of 6. What do you think that could be due to? So 6 protons, where could they come from? 2 methyls? Okay. Right? So that could work. All right, and then we know that this carbon right here, how many protons are coming off of that carbon based on the signal splitting for those 6 protons? 0, right? So that purple underlying carbon can't have any protons on it, because if it did, we would expect that peak to be split for those 6 protons. Okay, so let's make a note over here that it must have no protons. Okay. So we can go ahead and we can say, all right, that means that we must have 2 R group attachment points. We don't know exactly what they are though. All right, and then we need to then account for these remaining pieces over here. So we've got a 2 to 3 quartet and triplet. What the heck could that be? Yeah, quite often you start seeing these patterns, right? When you've got a quartet to triplet in a 2 to 3 ratio, that's a big clue that it's an ethyl group. So maybe over here, maybe it's something like that. All right, so have we accounted for all of our carbons? Yeah, I think so. We've got 5 carbons accounted for. We've got our oxygen accounted for. Do we have our hydrogens all accounted for? Yeah, I think we've got everything accounted for. So now what we need to do is we need to, again, link this all together. Well, this makes sense, right? Because we said over here that we had these two groups. And then over here, maybe an oxygen and alcohol is coming off the other. And then over here, maybe it's this. This would be the correct answer for that one.
So those two methyl are in the same environment.
Yeah, so these two methyl groups are going to be equivalent to one another because there's actually a plane of symmetry for them. If you build this as a model kit, you'll see that there's a plane of symmetry where they're mirror images of one another. Yep, good questions. So some of these are a little bit tricky.
Yeah.
I find the biggest challenge is keeping yourself calm, not letting your brain lock up on you. So if you do get to the point where you're just stuck, sometimes, I'll be honest, it's best to walk away, work on other problems, and then come back to it, but don't give up on it. Just stay calm. All right, I'll post this video too. Hopefully this helps other people as they're working through some of these.